Let's talk about standard deviation and variance, concepts and terms you've probably heard before, but let's go into a little bit more depth about what they really mean and how you compute them. It's a measure of the spread of a data distribution, and that'll make a little bit more sense in a few minutes. Let's talk about standard deviation and variance, two fundamental quantities for a data distribution that you'll see over and over again in this course. So let's see what they are if you need a refresher. Again, let's look at a histogram because variance and standard deviation are all about the spread of a data, the shape of the distribution of a data set. So let's take a look at this fake data. Let's say we have some data on the arrival frequency of airplanes at an airport, for example. And this histogram would indicate that however we choose to quantize that data, let's say we have around 4 arrivals per minute. Well, that happened on, say, around 12 days that we looked at for this data. So 12 different discrete data points at 4 arrivals per minute-ish. But then we had these outliers. We had one really slow day that only had 1 arrival per minute, and we only had one really fast day where we had almost 12 arrivals per minute. So again, the way to read a histogram is look up the bucket of a given value, and that tells you how frequently that value occurred in your data. And the shape of the histogram can tell you a lot about the probability distribution of a given set of data. So we know from this data, it's very likely to have around 4 arrivals per minute, but it's very unlikely to have 1 or 12, right? And we can also talk specifically about the probabilities of all the numbers in between. So not only is it unlikely to have 12 arrivals per minute, it's also very unlikely to have 9 arrivals per minute. And once we start getting around, 8 or so, things start to pick up a little bit. So a lot of information can be had from a histogram, and the variance just speaks to how spread out, what is the shape of that data, how spread is your data set. How do you measure variance? Well, we usually refer to it as sigma squared, and you'll find out why momentarily. But for now, just know that variance is just the average of the squared differences from the mean. So to compute the variance of a data set, you first figure out the mean of it. So let's say I have some data, it could represent anything. Let's say maximum number of people that were standing in line for a given hour or something. I don't know. And the first hour I observed 1 person standing in line, then 4, then 5, then 4, then 8. Okay? So the first step in computing the variance is just to find the mean, the average of that data. I add them all together, divide it by the number of data points, and that comes out to 4.4 is the average number of people standing in line. Now the next step is to find the differences from the mean for each data point. So I know the mean is 4.4, so for my first data point, 4.4, and I have 1, so 1 minus 4.4 is negative 3.4. 4 minus 4.4 is negative 0.4, and so on and so forth. Okay, so I end up with these both positive and negative numbers that represent the variance from the mean for each data point. Okay, but what I want is a single number that represents the variance of this entire data set. So the next thing I'm going to do is find the square differences. So I'm just going to go through each one of those raw differences from the mean and square them. This is for a couple of different reasons. First of all, I want to make sure that negative variances count just as much as positive variances, right? Otherwise, they would cancel each other out, and that would be bad. I also want to give more weight to the outliers. So this amplifies the effect of things that are very different from the mean while still making sure that the negative and positives are compared comparably. So let's look at what happens there. So negative 3.4 squared, positive 11.6, negative 0.4 squared, much smaller number, 0.16, because that's much closer to the mean of 4.4. 0.6 also close to the mean, only 0.36, but as we get up to the positive outlier, 3.6 ends up being 12.96. Okay? And to find the actual variance value, we just take the average of all those squared differences from the mean. So we add up all these squared variances, divide it by 5, the number of values that we have, and we end up with a variance of 5.04. Okay? That's all variance is. Now, typically we talk about standard deviation more than variance, and it turns out standard deviation is just the square root of the variance. It's just that simple. So if I had a variance of 5.04, the standard deviation is 2.24. So you see now why we call it variance sigma squared. It's because sigma itself represents the standard deviation. So if I take the square root of sigma squared, I get sigma. That ends up in this example to be 2.24. This is a histogram of the actual data we were looking at. Now, we see that the number 4 occurred twice in our data set, and then we had 1, 1, 1, 5, and 1, 8. Now, the standard deviation is usually used as a way to think about how to identify outliers in your data set. So if I say, if I'm within one standard deviation of the mean of 4.4, that's considered to be kind of a typical value in a normal distribution. But you can see in this example, the numbers 1 and 8 actually lie outside of that range. So if I take 4.4 plus or minus 2.24, we end up around there, and 1 and 8 both fall outside of that range of a standard deviation. So we can say mathematically that 1 and 8 are outliers. We don't have to kind of like guess and eyeball it. Now there is still sort of a judgment call as to what you consider an outlier in terms of how many standard deviations. So you can generally talk about how much of an outlier a data point is by how many standard deviations from the mean it is. So that's something you'll see standard deviation used for in the real world. There is a little nuance to standard deviation and variance, and that's when you're talking about population versus sample variance. Okay, just one little minor difference. So if you're working with a complete set of data, a complete set of observations, then you do exactly what I told you. You just take the average of all the squared variances from the mean, and that's your variance. But if you're sampling your data, if you're taking some subset of the data just to make computing easier, you have to do something a little bit different. Instead of dividing by the number of samples, you divide by the number of samples minus 1. Okay? So let's look at this example. In the example we just had, the population variance is exactly what we did. We took the sum of the squared variances and divided by 5, the number of data points that we had, to get 5.04. But the sample variance, which is designated by s squared, is divided by 4 and minus 1. So we took the number of data points we had, subtracted 1, and got the sample variance, which comes out to 6.3. So again, if this was some sort of sample that we took from a larger data set, that's what you would do. If it's the complete data set, you divide by the actual number. Okay, and that's the difference between population and sample variance. As for why, it gets into like really weird things about probability that you probably don't want to think about too much. And if you want to express this in terms of fancy mathematical notation, I try to avoid notation in this course as much as possible. I think the concepts are more important. But this is basic enough stuff that you will see it over and over again. Population variance is usually designated as sigma squared, where sigma is standard deviation. And we can say that is the summation of each data point x minus the mean mu squared. That's the variance of each sample squared over n, the number of data points. And sample variance, similarly, is designated as s squared. And that is the summation of each data point minus the mean m of the sample set squared over n minus 1. So you subtract 1 from the number of samples that you have. That's all there is to it. So let's look at some real examples and write some Python code to make this happen. Let's write some code here and play with some standard deviation and variances. So if you pull up the Variance Python notebook, standard deviation variance file, follow along with me here. Please do, because there is an activity at the end that I want you to try. So what we're going to do here is, just like the previous example, we're going to use matplotlib to plot a histogram of some normally distributed random data. And we're going to call this, well, we're calling it incomes, and we're saying it's going to be centered around 100. Hopefully that's an hourly rate or something and not annual, or it's some weird denomination, with a standard deviation of 20 and 10,000 data points. So let's go ahead and generate that and plot it. And there you have it. So we have 10,000 data points at centered around 100, as you can see here. So with a normal distribution with a standard deviation of 20. So that's a measure of the spread of this data. And sure enough, you can see that the most common occurrence is around 100. And as we get further and further from that, things become less and less likely. And the standard deviation point of 20 that we specified is around there, around there. So you can see that's kind of the point where things start to fall off sharply, right? So we can say that things beyond that standard deviation boundary are unusual. Now, NumPy also makes it incredibly easy to compute the standard deviation and variance. If you want to compute the actual standard deviation of this data set that we generated, you just call the std function right on the data set itself. So NumPy, when it creates a list, it's not just a normal Python list. It actually has some extra stuff tacked onto it. So you can actually call functions on it like std for standard deviation. And we can do that, and we should get a number pretty close to 20, because that's what we specified when we created our random data. We wanted a standard deviation of 20. Sure enough, 19.96, pretty close. And the variance is just a matter of calling .var, which comes out to pretty close to 400, which is 20 squared, right? So the world makes sense. Yay. Standard deviation is just the square root of the variance. Or you could say the variance is the standard deviation squared the other way around, and sure enough, that works out. So the world works the way it should. Now I want you to dive in here and actually play around with it, make it real. So try with different parameters on generating that normal data. Remember, this is a measure of the shape of the distribution of the data. So what happens if I change that center point? Does it matter? Does it actually affect the shape? Why don't you try it out and find out? Try messing with the actual standard deviation there that we specify and see what impact that has on the shape of the graph. So if I wanted a standard deviation of 30, I could change that there, and you can see how that actually affects things. Or let's make it even more dramatic, like 50. Just play around with it. You can see it's starting to get a little bit fatter there, right? So play around with different values. Just get a feel of how these values work. This is the only way to really get an intuitive sense of standard deviation and variance. Mess around with some different examples and see the effect that it has. So play around with this a little bit. See you in the next lecture. So that's standard deviation and variance in practice. Got your hands on with some of it there. So hope you played around with that a little bit to get some familiarity with it. Very important concepts. We talk about standard deviations a lot throughout the course and throughout your career in data science. So make sure you got that under your belt. Let's move on.